Humanity hasn't traveled beyond low Earth orbit since the final Apollo mission in 1972. When the Space Shuttle program ended in 2011, the United States lost its ability to launch its own astronauts into space. Thousands of jobs vanished from the Kennedy Space Center, property values collapsed, and the surrounding cities began to feel like ghost towns. Building a permanent presence on the Moon requires NASA to integrate heritage components, like the shuttle's main engines, into a completely modernized flight architecture, slapping the analog dials of the 60s for high-speed digital control systems. This mission is the catalyst for a regional recovery, creating 13,000 new jobs as NASA attempts to prove these updated systems are ready for deep space. That recovery has already provided a $6 billion boost to the local economy ahead of the April 1st launch window. Private partners like SpaceX and Blue Origin are now a permanent part of the landscape, building the infrastructure needed to reach the lunar surface. At PAT 39B, the Space Launch System, or SLS, is fully assembled and fueled. Weather officers estimate an 80% chance of favorable conditions. Over 400,000 spectators are expected to line the Florida coast to watch the first crewed flight of this program. The ticking countdown clock marks the end of a long domestic drought, moving the focus to the survival of the 4 people on board. The SLS rocket uses 4 RS-25 engines with Space Shuttle heritage, generating 8.8 million pounds of thrust to lift the 98-meter-tall vehicle. Inside are Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, the first crew to test these integrated digital flight controls in a real-world environment. They've named their zero-gravity indicator RISE, a tribute to the iconic Earthrise photograph taken during the Apollo 8 mission. Once they clear Earth orbit, the crew relies on the Orion spacecraft to manage the complex burns required to reach the Moon. Surviving the ascent is just the first step. The true test of their software-driven navigation begins in the vacuum 460,000 kilometers from home. The mission uses a free return trajectory. The capsule will slingshot around the far side of the Moon, using lunar gravity to pull it naturally back toward Earth. During this coast, every system, from life support to thermal regulation, is monitored by automated software to ensure it can sustain a crew in deep space. The mission also carries an avatar organ-on-a-chip experiment, which uses living cells to study the effects of high-energy cosmic radiation. By tracking how these cells react to microgravity and deep space radiation, scientists can gather the data needed to protect future astronauts on the way to Mars. Artemis 2 isn't about landing. It is a specialized mission to find the hardware and biological limits we have to solve before we can stay. On the return trip, Orion will hit the atmosphere at 40,000 kilometers per hour. The heat shield must manage temperatures reaching 2,800 degrees Celsius, using advanced thermal protection to ensure the crew makes it to their Pacific Ocean splashdown. While Apollo crews relied on manual analog switches and paper charts, this return is managed by an integrated flight computer that processes thousands of data points every second. A successful landing clears the way for Artemis 3 to return humans to the lunar surface, and for the launch of the Gateway station in orbit around the Moon. This 10-day flight proves that the integration of heritage hardware and modern digital systems is working, moving us from the era of short visits to a future of permanent habitation.